Okay, thank you for the invitation, and thanks for coming to this talk. So I'm going to talk about a framework for personalizing and testing decisions, and let's just start with a motivating example. So the example is a project that I worked on several years ago. It's relatively dated, but it has all the ingredients that I need to make for the presentation. So it's about hospital readmissions. So that just a motivating example. So when a patient leaves a hospital, within 30 days, if they come back, right now in the US, the government basically penalizes hospitals if that happens very frequently, and their payments get adjusted for that. And this is a phenomenon that is actually pretty common. The cost of that to Medicare, this is the latest number. It used to be like a bit larger number, but so the annual cost of that to Medicare is about $20 billion, and a single readmission visit costs about $20,000 on average. Now, because of these incentive changes and the fact that hospitals became interested to take actions, so a series of potential interventions have been introduced called like post-discharge support programs, for example. Like it could be like a, telehealth solution that monitors patients' symptoms when they are at home, or creates a channel between patients and nurses so they can communicate if there's a problem. Now, let's say there is a telehealth solution or some solution. It could be even like follow-up phone calls. But let's say there is a very pricey but effective solution. So it costs about $2,000, $200 per patient, but it can actually reduce the expected cost of a readmission from $20,000 to $12,000. So then the whole question becomes, how should I use it? Like, who should get this? I can't give this to everyone. It's going to be expensive. I need to somehow allocate this expensive but effective resource. So the whole question is, the decision question is, how to allocate this intervention. And now the ML approach, which I'm not going to go through in detail, but there's been a lot of like papers and solutions by companies, for example, that say, let's take a patient, look at all the electronic medical records or other potential information you have them about these patients. And a patient is like a vector, a very large vector of all these features, and use ML to look at past data to predict probability of readmission given these features. And once you build this model using all sorts of high-tech machine learning methods, and you have these probabilities, then the next step is, now let's take these probabilities and take action. So these probabilities would basically say, if a patient has a risk score between 100%, say, to, 0%, and the high-risk patients should get the intervention. So just to give you benchmarks for this specific, these are all real data based on a hospital in DC. If the intervention was not going to be applied to anyone, so imagine, let's try to see the baseline. The baseline is we don't do anything. So what's going to happen is some patients will be readmitted. So for those, we're going to end up with a $20,000 charge. In expectation, per patient, we're going to end up with about $5,100 charge. The other alternative is give the intervention to every single patient, which is something that a lot of hospitals do because they believe, if it's a good solution, why not? Why should we give it to only a subset of patients? So that turns out the overhead cost is that $2,200 costs of the intervention per every single patient will actually outweigh the potential benefits you're going to get on the cost reduction. So you end up actually spending a little more per patient by giving it to everyone. So for sure, we increase quality of care. Like this bullet has a much better quality of care than this one, but we have ended up paying more. But if you do this ML approach of do the intervention, only give it to the patient that have a high risk above certain threshold, then we showed in this paper several years ago that you can actually end up with $4,300 per patient. For that single hospital, it would translate to about $300,000 savings per year. So this is just like some like a simple use machine learning for a targeted decision making. There is nothing really fancy here, but the numbers really show that if you do this targeted type of decision making, you get the benefit. Now, this is not alone. Like, in fact, there's a large literature on use ML in the healthcare space to allocate costs. For example, septic shock. You want to predict which patients in ICU will develop sepsis, and then you could have a rapid response team that could go and help them. So use ML to allocate that costly resource of rapid response team. Whether it's acute lung injury, it's been applied in like I would say outside hospital, like for medication adherence, like pharma or population health management. You want to increase adherence to medication, predict which patients are not going to take their meds, and then have some kind of intervention applied to them. So many other things. This list is massive. Like, I only have like some of examples. I started actually these projects, like the one in the previous slides, about 10 years ago. And I really thought by now most hospitals, health organizations are going to be using these technologies. But in reality, the adoption is pretty slow. It's very slow. Most of them are just, they made it, like, we only know about them because there's a paper, but that's it. You do hear there are startups or large companies, they talk about them, but in reality, if you go to hospitals, adoption of these technologies is very limited. Now, there are many reasons why these adoptions are limited. There are incentive reasons, like if, for example, you may argue that, in fact, this whole readmission thing that I mentioned, nobody cared about them before Medicare started penalizing hospitals. So you need to have the incentives in place so the healthcare organizations decide to take actions. And you could argue that the incentives are still not strong enough. Like in the readmission case, the amount of penalty per year may end up being not more than the solutions that a company would try to sell to a hospital. So it's not cost effective for them. They would rather to pay the penalty. So the incentives are not quite fixed. But even if you go to an organization like Kaiser, where the incentives are right, like they are paying for the cost themselves, you still, they are using some of these techniques, but it's not even comparable to what you would expect in the high-tech, like advertising or other type of industries. So some aspects of it are cultural as well, like you need to integrate these into workflow. But there are also methodological issues. Like everything I said so far in the previous slides, I'm going to argue, because this is a data science workshop, I'm going to talk about some data science or methodological challenges, actually, things that we did not take into account when I demonstrate to you this potential solution. Any question, by the way, so far? Okay, so other than the incentives, culture, and like workflow modification, etc., there are methodological problems with what I said so far. And I'm going to try to talk about 3 of them. There are 3 assumptions that I made that are actually not true. Assumption 1, I assumed effect of the intervention is known. Meaning I actually know, remember I said I know that when I use the telehealth solution, the expected cost goes from $20,000 to $12,000. This is an assumption that we make that I know that, in fact, that's not true. Maybe somebody used an intervention like that in a hospital in a different part of the country and they got that much cost reduction. It's not guaranteed that I'm going to get the same cost reduction in my hospital. So the effects are not really known. They need to be tested in your organization. 2, I assumed effect of the decision or that intervention is fixed per patient, meaning every single patient, the expected cost goes from $20,000 to $12,000. That's not really true. Some patients may benefit a lot from a telehealth solution, and some patients may not at all benefit from it. So the effect of the decision needs to be calculated per patient. And then the third one is data is collected adaptively. And this is something that is becoming more of a problem. And I'm going to try to, like from a math perspective, we say samples are actually not independent. Let me just elaborate a little bit on this. So we have hospital electronic medical records. Data goes to a machine learning engine. Machine learning engine makes predictions at the point of care, and then physicians take those predictions into account and make a decision. So I talked about like the readmission case, but in the, say, sepsis case or other things, the decisions of what to do next depends on what the ML engine told the doctors. So what's going to happen is now this decision will be the future data that the engine will use tomorrow to retrain, or tomorrow or a week from now or a month from now to retrain the algorithm for the future cases. So in reality, when we are making a decision here, or when ML algorithm makes a recommendation, we need to keep into account that whatever we do will impact our future learning. And that's pretty much ignored, as far as I'm aware of, in everywhere these applications are applied. And in fact, this will create what we call a correlation across samples, or when data is adaptively collected. So methodologically perspective, at least in the first part of the talk, we did not take into account any of these issues. So I'm going to try to discuss a framework that includes these three aspects. Any question? Yes?
If I may, the hospital EMR is a static record. A patient walks in, that's when the EMR record gets updated. The patient doesn't walk into the hospital, the EMR does not get updated. So the sample that you're going to choose is going to be static in nature and itself. If you're looking from a remote patient monitoring perspective, then a patient is actually wearing a Fitbit or has an Apple Health or a home dialysis machine or blood pressure monitor, and it updates the EMR record. That's when machine learning algorithm has got a higher sense of precision and record.
So let me elaborate. The EMR is not a static if you look at it over like a week period or over a month period. So the patient comes in today, the EMR is not changed, right? But as soon as the patient leaves, the EMR is updated. And then once the EMR is updated with this current patient's information, then the engine tomorrow, or it depends how often they retrain these algorithms. At the time that they retrain the algorithm, that update will impact the ML engine.
Right. So your hypothesis, if I may, is to make sure that you are assuming that the hospital EMR is a non-static record and it will continue to grow on a weekly basis, and the ML algorithms are going to be trained on a weekly basis. And then.
Yes, I'm going to give you a very clean example that, in fact, why decisions will go wrong with this kind of feedback. Thank you, Erica. Yeah, so I have 5 minutes. So let me just try to, okay, so let me just first talk about the first bullet that I said I know the effect of the decisions, right? So in fact, let's say I don't know the effect of these two decisions. Like I go try to answer the first bullet. Like I have two different solutions and I don't want to know which one is the most effective one. So the best way to do this is run an A/B test or a randomized control trial. But in fact, good luck to get approval to do this in a healthcare organization. It's considered unethical or very expensive. Like only through like FDA drug trials that are very expensive, you can get this type of approval. How many of you here are familiar with this kind of like RCTs or A/B tests? Like I just want to make sure the terminology is clear. We just randomize a decision. Good. So randomize the decisions. Okay. So in a healthcare organization, this is pretty hard to do. But if you go beyond healthcare, companies run tens of thousands of these every year. And the number keeps growing. Like for every type of decision, they just test it. Let's just test this thing work? Go through a rigorous test. And in fact, this is where really healthcare is failing compared to high-tech world. We are not testing new innovations very quickly to just figure out what works, what doesn't work. We keep testing. We have a training set and a test set, and that's it. Or maybe we will have a prospective evaluation. But kind of a real A/B test of checking high-tech solutions, do they work or not, really means something like this. But even in the companies, they are worried about this. Like it's not the case that these things come for free. Like a company like Facebook will be having a PR problem because they're experimenting with users' emotions. So even in the high tech, like a company like Facebook, experiments are not free. I did say they do a lot of them, but even they're worried about them. And because of that, they've been using what's known as these multi-arm bandit experiments. So multi-arm bandit experiments, and in fact, this is a Google Analytics page that explains for publishers how it works. Let me just, given the limited time, just shake like a one-slide summary of that web page written for advertisers. It basically says, if I run an A/B test versus a multi-unbanded experiment, you end up needing 80% less samples, which means 80% less traffic is used to figure out which one of A and B is better. And that translates to about 97.5 conversions that are not wasted. So the opportunity cost of this experiment is reduced significantly. And mathematically, there is theory that says, an A/B test opportunity cost grows linearly in the number of samples, but NAB's multi-unbanded experiments opportunity cost grows logarithmically. Now, then in our group, we've been trying to extend these to, so far we talked about the first bullet, testing the effect, just figuring out the effect. But now the personalization comes into play, and when you do personalization, then you have to think about that A is optimal for a subset of patients, and B is optimal for the remaining ones. So we need to make that assumption. Thank you. So basically, just to try to get to the punchlines, it turns out in this simple case, let me try to. So this logarithmic in n that I talked about, which is the benefit of going with multi-unbanded experiment, it turns out when you personalize, that gets much worse. So like if p is the number of covariates or features that you're trying to learn, then the logarithmic n is actually not the problem. Is this number of parameters that you're trying to learn is a problem, and we introduced a solution that it doesn't grow with p and grows with a number of relevant features. But let me just, given that I have a minute and a half, let me just give you an example. So the example we applied this is warfarin dosing. So warfarin is a blood thinner, very prevalent, and the decision to make is there are 3 decisions. So here it's not an A/B test, it's like A-B-C test. I have 3 decisions for every patient to make. Put them on low dose, medium dose, or high dose. And this decision is really personalized. For some patients, high dose is better. For some patients, low dose is better. It's not the case that everybody gets the same dose. And there are these trade-offs. So the goal is how to decide the initial dose. So we applied this framework and some publicly available data, about 5,500 patients with 93 covariates per patient. And we basically compared different algorithms and our proposal. And we also compared with physicians' decision. Physicians always start a patient at a medium dose. So we compared with that. And this chart really summarizes the result. So look at the x-axis. X-axis is, imagine we are running the experiment and patients arrive to us one by one. And y-axis is the fraction of mistakes we make. So a patient comes in, we put them on a certain dose bucket, and we observe the outcome. And then we update our model and make better decision for the next patient. So we're going to make mistakes initially, and then the number of mistakes will go down. So this is what physicians would do. For 46% of the patients, they were going to make a mistake because 54% of population are medium dose, but not the remaining. But and this is the best you can do. So these are not realistic. This is what we call oracle. Like if somebody has access to all of this data in advance, then they can actually make about 33%. So the best you can do is really 33%. And then the algorithm we propose is this one. And it basically, after seeing about 200 patients, it outperforms physicians. And then eventually it gets closer to this line. But these are various other benchmarks from this literature that just are slower in terms of learning. And I think my time is up. I had a lot more to say, but I just want to say, we have introduced a framework for decision making that captures 3 things. I did not actually have any time to cover this one, like how we fix this one, but I did touch about these 2, the effect of personalization, and then how to test the not knowing the effect of the decision. And of course, in terms of theory, we have developed some theory for some of the latest methodology in this literature. Thank you.